Good morning, everyone. My name is João Carvalho, and the title of my presentation today is named Multidisciplinary Design and Optimization of Hybrid Electric High Spec Ratio Strut Braced Wings. So the motivation of my work is, it's supported by the aircraft climate emergency, so with the objectives of Europe to achieve carbon neutrality and also to reduce greenhouse emissions. So with these objectives and taking into account that traditional aircraft and most of the civil aircraft still has traditional configuration, meaning cantilever wing, there is the need to expand the design space if we want to meet increasingly stricter requirements in terms not only of performance and efficiency, but also in terms of noise emissions and the overall air quality. So this is an opportunity here, and in this project in Indigo, which is a project I've been working, and also on my thesis, we chose this non-conventional design, the strut braced wing, which consists of a cantilever wing with an extra wing, which we call strut, that basically supports the main one, and that from a structural point of view allows to minimize the bending moment of the main wing near the root, so having wings with higher aspect ratios and therefore maximizing the aerodynamic efficiency. So this is the idea, and like you saw on the title, this is a multidisciplinary design and optimization presentation, but one of the modules that was developed in-house was the structural model and the weight estimation, and we basically here did this hybrid approach in which we have a primary structure that is shown on the figure, where it's basically the wing box of the wing and strut with the adjacent fuselage, and then we have a secondary structure which is basically everything else, including control surfaces. And we do this hybrid approach in which we use a physics-based model to estimate the weight of the primary structure, because legacy weight estimation methods are mostly just accurate for conventional designs. So we had to come out with this physics-based approach. The power plant and electric masses are estimated using a surrogate from one of the partners of Indigo. So the physics-based model is basically a global finite element model, the GFEM, that is generated automatically within the OptiStruct framework, and it is simple sizing optimization in which the wing and strut is divided in several panels, and then each panel thickness is optimized. We also considered composite materials with predefined stacking sequences, and the traditional load cases, which I will not explore in detail due to time constraints, but we also considered the traditional strength and buckling constraints, like in a traditional case. So the other most important module in detail of this configuration is that is hybrid electric. So we have parallel serial configuration in which we divide it into main parts, the inboard and outboard. So in the inboard, we have the gas turbine connected directly to electric machine that can function as a generator or a motor. So if it's a generator, it extracts the mechanical power from the propeller to feed the electrical grid, and if it works as a motor, it goes the other way around, so it extracts the electrical power from the outboard part to feed the inboard propeller in this case. We also define here two control variables, so the local hybridization factor, we call it, to basically estimate how the electric machine works. So if it's working as a motor or as a generator, and also a thrust split, because we wanted the MDO framework to allow to have to give more freedom to the optimizer to find the optimal division of thrust between the inboard and outboard part. So this is the tool that we have here. It is also an inboard tool. In this case, it doesn't use the traditional OpenMDO framework that everyone is used to. We use the GEMCO, so a French framework, European, that supports gradient-based and enables coupled multidisciplinary analysis and has this interesting feature that allows automatic differentiation using this JAX plugin. So this is a simplified scheme of what we have. So a first model in which we have the aircraft geometry where the weights are defined, the mass is positioned to, and the center of gravity are also estimated. And then takeoff analysis and landing analysis where these two segments are evaluated. And then a mission analysis where the steady flight phases are basically performed. So zooming on that, we also integrated several models from several partners. So in the aerodynamics, we estimate the aerodynamic coefficients that feed a module where the aircraft is trimmed. And then in that module, we get the required thrust that feeds the propellers. And then from the propellers, using the hybridization factor, there is a power that goes to the inboard part and a power that goes to the outboard part. And the most important output from the power plant, in our case, is the mass flow rate and the emission flow rate, but also the variation of the battery state of charge, which are integrated next so we can have the total weight of each pollutant and fuel. Just a quick module also presentation. We have this noise evaluation feature that is a low fidelity coming from DLR. We have this EMMIS plus in-house program from DLR, which is basically a low fidelity tool in which they model each propeller as a point source with directivity, and we are using this tool to train a surrogate. So we train a surrogate for a propeller varying the diameter, the power, and the rotational speed, and then after we evaluate and creating this surrogate for each propeller, we do this summation. So it allows us to have different variations in terms of number of propellers along the wing, and then we have this correction in terms of altitude because this surrogate was trained for a different altitude than the ones we are considering. So this brings us to the case study presented here, in which we basically want just to evaluate the trade-off between block fuel and noise. And like I mentioned earlier, the noise we are considering comes only from the propellers, so we are not considering fuselage, landing gear, so it's still a preliminary stage in that sense. And this is the mission we are considering, so 1,000 nautical miles nominal mission with a 400 nautical miles diversion part, and these are the cruise conditions, so 8,000 meters altitude and 0.6 max cruise with a fixed MTOW and payload. To do this study, the option was to optimize the block fuel, but doing the Pareto in a way that we can have a step in terms of noise constraint. So we have a noise constraint that gets strictly more demanding, and we were able to create that Pareto. It is basically the design space in which in this case, we kept the airframe fixed, but we are optimizing all the design variables within the power plant, and also the control design variables in terms of hybridization factor and a thrust split factor. Also the propellers and some failure cases that I skipped due to time constraints. And the optimization constraints are the traditional ones in this type of aircraft design presentations. So I will also skip this part. And this is basically the Pareto front that we got. So from the unconstrained noise case to the maximum constrained one, we get 7.7% increase of fuel. So the main conclusion is that quieter aircraft is feasible, but it has a cost associated to it. So we try to analyze the design variables behavior to see if these optimization
João,
results made sense physically.
You need to finish as soon as possible.
Okay.
10 minutes already.
So the idea, the idea very quickly is that the noise was decreasing by reducing the propeller rotational speed, which would lead to an increase of the thrust coefficients to compensate for the lack of thrust due to the reduction of that rotational speed. And then we can see here for different noise constraints that the propeller efficiency decreases with stricter noise constraints because the propeller operating point changes along the mission and gets further away from the peak efficiency zone. So that is one of the reasons why the block fuel increases, and the other one is that this is the last slide. This is the last slide. Is that the thrust is shifting to the outboard propellers, and that makes the overall efficiency decreases because there are a lot of losses associated to the electrical part in terms of the electric conversion and transmission losses, which combined with a decrease of the propeller efficiency explain this increase in block fuel. In terms of achievements, I have these scientific publications, and most of my work has been dedicated to this project. Thank you very much for your attention, and if you need any questions, just let me know.